Hello and welcome to this introductory tutorial to the Numeris Model Builder, a software platform that lets you build and run models in a wide range of paradigms. This tutorial will go through the steps of building a discrete density-dependent population growth model, one of a really interesting family of models. In the process, you will learn what a discrete model is and how it differs from continuous time models. To demonstrate how to build such a model in Numeris, we will be considering the Beverton-Holt fishery model. We will run this model and use Numeris' auto mode feature to dynamically explore the effects of changing parameters on model behavior. In this case, it is a great way to see how making small adjustments to parameters can produce a qualitatively different behavior and sometimes dramatically different behavior, including chaos. This is surprising and maybe even extraordinary given how simple the equations in this model actually are. Before building the model, I will ask my friend Andy to discuss the difference between continuous and discrete models and introduce the Beverton-Holt equation and describe its features.
Hello, and let's begin by reviewing the terms density-dependent and discrete. If you saw the last tutorial, you should remember that density dependence is a type of growth pattern where the growth slows down as you approach a threshold, often called carrying capacity. And if you somehow overshoot carrying capacity, the rate of change will actually become negative and the population will drop down until it reaches that carrying capacity. Density dependence is a term from ecology, but we see similar saturation functions in a variety of fields and systems. In this tutorial, we'll be building another simple density-dependent population model, but what will be different about this one is that we'll be using a discrete representation of time instead of a continuous representation of time. Now, what's that all about? Well, whenever you're modeling how a system changes, there are basically two ways you can model time. What we saw in the last example is a continuous representation of time. And the heart of a continuous time model is one or more differential equations that tell you how the state variables, or in our case stocks, in the model are changing at any instance in time. So here's an example of a differential equation. At any moment in time, this equation tells us the rate of change of x, which is great for a model because it produces very smooth curves and we can compute the value of x and the change of x at any given microsecond. However, sometimes we don't have good information about how something changes, or it simply isn't easy or maybe even necessary to determine the instantaneous rate of change. In these cases, the next best thing we can do is to come up with an equation that tells us the value of something at the next time step based on what it was at the previous time step. That type of equation is called a difference equation as opposed to a differential equation, and its general form looks something like this. So in other words, the value of x at time t plus 1 is some function f of the value of x at time t. Now what the function f looks like depends of course on the model. It can be very complicated or very simple. But let's look at a simple one. In this difference equation, we're saying that the value of x at time t plus 1 is some constant lambda times the value of x at time t. So for example, if the initial value of x is 10 and lambda is 2, then the value of x at time 2 will be 20 and the value of time 3 will be 40 and so on. This is the counterpart of exponential growth. Although because this is a discrete model, we typically don't call this exponential growth, but we use the term geometric growth. So a couple things to note about discrete models. First, t is not explicitly part of the difference equation. We could be at time step 1 where t equals to 1 or t equals to 500. But the value of x only depends on the value of x at the previous time step as given by this difference equation. It doesn't depend on what the value of t actually is, or not usually. And the way computer programs simulate this type of model is simply repeating this equation over and over and over for as many times as you tell it. The second thing to note is that this equation only tells us the value of x at discrete moments of time, or whole number units of time, whatever those units of time might be. Our equation doesn't provide us any clues how it got from one value to the next. So if you give me the initial value of x and a difference equation like this one, I can use the difference equation to compute the value of x at time t equals 1, and I can run the equation a second time to tell you the value at time 2, but don't ask me what the value was at time 1.5 because I have no idea, because my model doesn't tell me. It only tells me the values at the discrete time intervals. So this also means that when we go to plot our results, if we really want to be noble and righteous and true, we can only plot a series of points, not a line series, because our model doesn't tell us what was going on between the points. Now, these differences between continuous and discrete representations of time may seem like minor details that would only be of interest to nerdy modelers, but understanding them helps explain why the behavior of discrete models can be quite different, and why discrete models are often a better choice for a given problem. And I think probably in ecology and in population studies there are probably more discrete models than continuous models, because they're often a better representation of what we know about how the system changes. Okay, so let's look at a discrete model of density-dependent growth. There are several we could look at, but the one I want to show you was developed in the 1950s by two British fisheries scientists named Ray Beverton and Sidney Holt. This is the difference equation they came up with, which is now appropriately known as the Beverton-Holt model. This particular version of their equation is actually called the generalized Beverton-Holt model because it has this extra gamma term up here, which I'll explain in a bit. So this equation might look a little bit complicated, but it really isn't if we take it apart and see how it mimics density dependence. There are basically three parameters here. We have R, which is the intrinsic growth rate, K, which we can think of as carrying capacity, and this gamma term, which is a scaling factor. Now, ignoring the denominator for a minute, we can see that this top part is simply geometric growth without any kind of bounds. When the intrinsic growth rate R is greater than 1, R times x of t will be bigger than x of t, and the population will grow. When R is less than 1, each value of x will be smaller than the previous time step, and the population will decline to 0, regardless of whatever is going on down here with the carrying capacity. Now, if we look at this denominator, there's two terms. And because this 1 is here, and because this term is always going to be positive, the effect of the denominator will always be to reduce the value of the numerator. When x of t is small relative to k, this term will be very small, and the dampening effect on the numerator will be quite small, and it'll basically be growing at the intrinsic growth rate, or just a little bit less. As x of t gets close to k, this term will get bigger and reduce the value of the numerator more and more. If x of t gets larger than k, in other words, the population overshoots its carrying capacity, this term will be larger than 1 and the dampening effect of the denominator will be even greater. And as soon as the denominator gets bigger than the intrinsic growth rate r, x at t plus 1 will be smaller than x of t and the population will decline. Now this gamma parameter is a scaling parameter that we get to pick. We usually pick values of gamma greater than 1. Now when gamma is greater than 1, gamma will reduce the size of this term when x of t is below carrying capacity and this term is less than 1. But when the population is above carrying capacity and this term is greater than 1, then a value of gamma greater than 1 will exaggerate or amplify the effect of density dependence and plunge x back down to the carrying capacity. Now, I won't get into any more details, but this gamma parameter is what makes this model generalizable, because gamma allows us to mimic different types of competition between individuals along a spectrum of what is known as contest competition on one hand and scramble competition on the other end. These are different ways that individuals compete for the same resource. And this is a very useful thing to do because intraspecific competition is one of the mechanisms through which increasing population size reduces growth. So if we have some behavioral information about our species, we can adjust the gamma parameter to better suit the organism that we're studying.
Thank you, Andy. It is now time to build the model. By now, you should be familiar with the basic steps of introducing components, linking with connectors, and writing equations. But let's first point out what is different about building a discrete model. First, since the state variable p, and we'll use p instead of x as we have in the earlier tutorials, since that variable is changing at discrete points in time, we want the flow's value to represent the next value of p rather than a change value added to the current value of p. We tell Numeris to do this by checking the sequence box in the state property pane. When we do this, we expect the flow expression to be a difference equation specifying how the next value of p is obtained from the current value. Finally, we are expected to use the discrete method in our simulation parameters. This is just the Euler method together with a dt of 1. Since the Euler method does a single update without trying to correct for errors of continuity, it is just a ticket. So let's proceed as before by dragging state and flow components onto the modeling canvas and making the flow connection. We will use a term for k and sliders for r and gamma, since we'll see the most interesting behavior occurs when we vary r and gamma. We then add connectors from r, k, gamma, and p to change p to indicate change p's dependencies on these parameters. Let's next program the sliders with reasonable ranges. Since we want r and gamma with initial values 1.5 and 2 respectively, we'll let them range up to 5 in steps of 0.1, with a minimum of 0.5 for r and 1 for gamma. And let's give k a value of 50. We can now insert the difference equation as the value of the flow change. Now here's an important technical point. Many programming languages express exponentiation using a caret, but this is not so for JavaScript. Instead, you must use the more cumbersome expression math.pow, in this case with arguments p over k and gamma. Sorry, but I don't make the rules. Understanding this, you see we have duplicated the difference equation in change p. Now we come to programming p. So we must check the sequence box and give it an initial value. In this case, we'll choose 10. Remember, the sequence box is crucial. This is a good time to save our model as we've done previously. Programming the simulation parameters is easy since we're using the discrete method. Let's choose an end time of 40 and see what happens. Lastly, we need a graph to show results. We should probably use a scatter graph since we're really only graphing at integer points. But the graph will be dense enough so that the connections won't be misleading. And now I will again turn to Andy to talk about the truly remarkable and unexpected things you see when you play with this model.
So if we're lucky, we can now run this model, and it does kind of what I expect it to do. It starts out with an initial value of 10. It increases fairly quickly because when x is small relative to k, this term has very little effect, and it increases, by 1.5 every time step, and then it kind of plateaus out at around 35. Now you might be asking yourself, well, why is it stopping at 35 when the value of k that we entered was 50, and isn't k the carrying capacity? Well, it's not quite that simple, and if we go back to our difference equation, we can see why that's true, is because the population isn't going to stop growing when p equals to 50. It's going to stop growing when this denominator term is equal to r, and then r over the denominator is 1, and that's what it means to not grow. And in this particular case, where we have r equals to, I think it was 1.5, and we have gamma equals to 2, that these two, the denominator and r are equivalent when p is approximately equal to 35. We could set r equal to the denominator and do a little algebra and find out the exact value, but our graph tells us it's approximately 35. Okay, so that was the hard part. The next thing we want to do is sort of play with this model and see how changing the values of the parameters changes the behavior of the model. But I'm really interested mostly in seeing the effects of r and gamma, because there's some kind of interaction going on between these terms. So let me go ahead and just kind of see what a different value of r. Let me crank r up to 2. Now what I would predict is that it's going to increase faster. It kind of looks like it's hitting 35 around maybe around the 7th time step. Let me exec that, and it does seem to increase, and it also increases the carrying capacity, or increases the top level to about 50. So it makes it all the way up there. Let me increase it a little bit more, maybe go up to 2.5 and exec again. And now this is interesting. It looks like we're getting a little bump up there when we make R larger. So to play with this a little bit more, I'm going to turn on auto mode. Auto mode is this button right here. And when auto mode is turned on, then when you move your slider, this graph should update sort of dynamically. And as I increase the value of R, I do and see actually some interesting behaviors up there. As R is now 4, which is a fairly high value, and we're seeing these oscillations. So let me zoom in to these oscillations a little bit more. And I can see that the population is peaking and then dropping back down. Now this is kind of interesting because we didn't see this kind of thing before when we had a continuous density-dependent growth model. If you remember the logistic growth model, the population sort of gradually approached carrying capacity, but it never did this kind of oscillatory behavior. And this is a really interesting kind of behavior that we only see with discrete population models, because our difference equation never says that the population can go above the carrying capacity. In fact, with a high value of R, it can sort of jump over the carrying capacity to the other side, and that's why we see these oscillations. You don't get that kind of behavior in a continuous population model. Now let's go ahead and let me bring R back down to something a little bit moderate, maybe 2.5. And I haven't played with gamma yet. We know that gamma is going to do some kind of effect on our denominator there. So as I increase gamma, looks like we're getting a similar kind of behavior. But whoa, something crazy is going on there, right? It gets to a point where the oscillations are no longer dampening, but they're actually sort of diverging. And I can zoom in here to look at that, which is kind of an interesting behavior. Let's see if maybe there's a combination of R and gamma where we could get stable oscillations. In other words, the final steady state of this system is not a single number, but actually, but as I increase R, it looks like we're getting to a range where we are seeing what appears to be stable oscillations. And if I increase gamma even more, now this is kind of an interesting behavior. If we zoom in here, it looks like we're getting a pattern, but it's not a two cycle oscillation. It's a 1, 2, 3, 4. It's like a 4-cycle oscillation. And maybe if we increase R, now we're getting something else. Maybe this is a, we'd have to investigate, but this could be a 16-point oscillation or an 8-point oscillation pattern. And when we get really large values of R, now what we see here is something very strange. And this is basically a pattern. It's a kind of oscillation, but it never repeats itself. And if we wanted to make sure that we just haven't let it run long enough, I can increase my end time. And now maybe zoom in out here. But when you see a pattern that looks like it's bouncing up and down, but it never ever repeats, this is a telltale sign of chaos. So chaos is a mathematical property, or it's a pattern where you have extreme sensitivity to initial conditions and a pattern which never repeats itself. But these are the types of complex, really curious behaviors that we get with discrete population models, from relatively simple equations. This is not a super fancy equation. It's just got 3 terms, and just small values or small changes in those parameter values gives us all kinds of qualitatively different behavior. So what we've seen in this example, just sort of playing around with it, are asymptotic stability, where it sort of gradually approaches a threshold. We've also seen 2 different types of cycling. We saw dampening cycles and then sort of stable limit cycles, where it sort of feeds into a sort of a steady pattern. We actually also saw diverging oscillations, which was another type of outcome. And then finally we saw chaos. So I would leave it to you to continue playing with this model and try to find other types of behaviors, and try to look at the equation and think about why we're seeing those different types of qualitatively different outcomes. So I'll stop there, but to summarize what we looked at in this tutorial, first of all, we learned that discrete models are defined at their core by a difference equation as opposed to a continuous differential equation, and that to create a discrete model, but what we have to do is we have to check the sequence property in our stock, and what that does, it means the value of the stock assumes the value of the flow, and we start calling it a sequence, and it turns a pretty pink color. We also need to change the clock to the discrete method, because that's the appropriate sort of method to get from time step to time step. And then finally we saw that discrete models are fun to play with, and they're actually quite common and very useful for a range of applications. So I hope you found this to be interesting. I invite you to continue playing with this model, and we'll end it there, and thank you for listening.